Section 4.4, Optimization and Elasticity of Demand. In the previous section, in 3.3, we learned about how the first and second derivative can be really useful and really effective at finding local maxima and minima of functions. So it turns out that this is a really helpful tool, and we can apply it to a lot of real-world situations. And this process we call optimization. Okay, because there are a lot of different functions that we might want to find a maximum value or a minimum value of. Like it would make sense if we had a cost function c of x. You could probably imagine examples where we'd want to minimize cost. Or if we have like a revenue function r of x, you could imagine us wanting to maximize that. There are also a lot of other examples that we'll run into, like say you're designing some kind of shipping container, right? Some kind of box, and you want to maximize the volume of this box, right? That would be like an optimization problem. Or maybe you're trying to design a shipping container and you have a certain volume that you want, but you're trying to minimize the amount of materials used. So you'll want to minimize the surface area. Okay, so optimization, there are a lot of different ways in which we would apply what we know about derivatives to help solve problems and or in business applications run things more efficiently. Okay, so let's jump into an example just to sort of familiarize ourselves with the process of optimization. This is a very common type of example. We want to minimize the product of two numbers whose difference is 100. Okay, so we have two numbers, right? So it might make sense to just define a couple variables because we don't know what these are. We want to find what these two numbers are. So maybe I'll let x and y be these two numbers. And generally in these problems, we're given some piece of information or some kind of constraint on these variables, and then we're asked to do something. We're asked to complete some kind of objective. So what we are told, the information or the constraint of this problem is the difference of these two numbers is 100. And the objective, the thing that we're trying to do, is we're trying to minimize the product. So we want to find two numbers who, when you take the difference, you get 100, but we want two numbers that do that such that the product is the smallest. So you multiply them together and you get the smallest possible output. All right, so to solve this kind of problem, we have to set up a couple different equations relating to the constraint and to the objective. So we call these equations, the first one is the constraint equation, unsurprisingly. Okay, so the constraint equation, and usually the constraint equation comes from using the variables we've defined, and it usually involves the piece of information, or if there's another number that's given in the problem, usually this appears in the constraint. So if these two numbers have a difference of 100, that's like the constraint, the requirement we have for these two numbers, how would we represent that using an equation? Well, difference means subtraction. So if I do x minus y, we want that to be equal to 100. So there it is. That's our constraint equation for this problem. All right, and then there's also the objective equation, and this relates to the thing we're trying to do. So here we're trying to minimize the product, so product being the multiplication of these two numbers. So over here I'm going to say, all right, here's our objective. And the objective is relates to the product. So I'm going to define the product. I'll just call it P. And this equation is pretty simple. P is just equal to x times y. Now what we're trying to do in this problem is we have this product and our goal is to minimize that. So we want to minimize the product P. And, like I said at the beginning of this section, we use first and second derivatives to, answer questions and find maxima and minima and things like that. So we'll probably want to find a derivative here, but we have a bit of a problem because we would want to take the derivative with respect to some independent variable, but we really have three variables here. We have P, X, and Y. So the next step, which I usually call the rewrite step, what we want to do in the rewrite step is we're hoping to express our objective as a function in terms of a single variable. So what I'd like to do is I'd like to rewrite P as like a P of X maybe, right? So just some function expressed in terms of the single variable X. Now how can I do that? How can I get rid of this Y if that's the variable that I'm trying to target and get rid of? Well, I have this constraint equation up here, which we defined at the beginning of the problem. And what I can do is I can use substitution here, because if I take the constraint, so here's our constraint, x minus y equals 100. And I can solve for y, like I can add y to both sides, subtract 100 from both sides, and x minus 100 is equal to y. And what I can do now is I can substitute in x minus 100 wherever I see y in my objective equation. So that's our constraint. Now going back to our objective, I can rewrite P as being equal to x times, instead of y, I'm going to put x minus 100. All right, and now I'm actually going to express P as P of x. So this is the goal. This is what we're trying to get to. We're trying to express P as a function in terms of a single variable. Because now that I have this, so this is like my rewritten objective equation, and now I can properly call it just a function in x. I can apply calculus. I could use the first derivative, find critical numbers, and find, in this case, the minimum, right? Because I'm trying to minimize this product P. So that's the next step. Now we want to minimize this function P of x. So I'll keep working over here. So I'll say finally, we can minimize P of x. Minimize just being find the minimum value. Okay, so how do we find a minimum? Well, usually we'll find the critical numbers, so finding the derivative of P would be helpful. I might rewrite P of x as x squared minus 100x. I just distributed the x into the parentheses. And I do this because it makes it a little easier to find the derivative rather than doing a product rule. I'd rather just do a couple power rules. So 2x minus 100 will be my first derivative of P. And I'm looking for the critical numbers, so I'll set this equal to 0. So now I'm finding the critical numbers. Okay, so I'll set this equal to 0. And, I'll add 100 to both sides, divide by 2. I get that x is equal to 50. Okay, so remember, what I'm doing here is I'm trying to find these two numbers, x and y, such that their difference is 100 and they have the minimum product. So 50 is one of these numbers. Okay, so what I have to do real quick is I have to do a little sign analysis, because this is a critical number, right? This is a point at which we have a horizontal tangent line, but remember, that doesn't necessarily guarantee that it's the minimum, because we have horizontal tangent lines at minimum values, we have them at maximum values, we even have them at these swivel points. Sometimes we'll get them at a point like that. So we have to do a very quick sign analysis. Okay, so this is a sign analysis for p prime of x. And I do these quickly because we should be pretty comfortable doing sign analyses at this point. Our critical number is 50, so remember we want to know what is the sign of p prime, the first derivative. So I could plug in 49 into the derivative and I get a negative number. And then I could put in 51 into the derivative. I'm plugging into this, p prime of x, and I get a positive number. And this is looking pretty good because it means that the behavior of p, the product, it's decreasing to the left of 50, increasing to the right of 50. That shows me that I have a local minimum right there at 50. So that's great. That confirms that this is in fact a local minimum. And the final step is just finding out what the other variable is, what y is equal to. Okay, so let me just draw a little line here. We're headed into the last step here. I'll say, so x is equal to 50. That means that 50 minus y is equal to 100. So I'm plugging back into the constraint equation to solve for y. I can add y to both sides, subtract 100 from both sides. So I'm getting that y is equal to negative 50. Okay, so I finally have my answer. The two numbers that we were looking for are positive 50 and negative 50. All right, so those are the two numbers whose difference is 100, who have the smallest product. Okay, and you can kind of test this a little bit, right? Because there are a lot of different numbers who have a difference of 100. Like, I don't know, you could have 101 and 1. Their difference is 100, right? Or 150 and 50. You take the difference of those two numbers and you get 100. But if you multiply those numbers together, you know, you're going to get a whole bunch of different products. These two, 50 and negative 50, are the two numbers that have the smallest product. All right, so that's our first example, just giving you the basic kind of flow of these problems. And here are the guidelines that we followed just a minute ago. So when we're trying to do one of these optimization problems, we usually start by finding an objective function and determining the constraints, and then using those constraints to rewrite the objective function with only one independent variable. All right, so that's what we're doing up here. And then we use calculus to find maxima or minima, depending on what we're trying to do. And then, you know, you're doing a little sign analysis, checking endpoints if it's applicable, right? Like if we have a sort of a restricted domain or something like that, we have to check endpoints because we could have a local maximum or minimum at the endpoints. Let's try another one. This one, we want to maximize the area of a rectangle with a perimeter of 20 inches. So drawing pictures is really helpful. A lot of these problems will have sort of a geometric element to it. We're talking about a rectangle. There's a rectangle. I'll label these sides. How about this is X and this is Y? We want to maximize the area of a rectangle with a perimeter of 20 inches. Okay, so I have my two variables defined here. right? Because what defines a rectangle is just its length and its width, so that'll be x and y. Let's see if we can come up with a constraint equation. Now remember, the constraint equation generally will involve any numerical value that's provided in the problem. That's common. Usually there's some number that defines a constraint, in this case on the perimeter of the rectangle. Okay, so if the perimeter is 20 inches, like how can we define an equation using our variables x and y given that the perimeter should be 20 inches? Well, the perimeter of a rectangle is just, the sum of all four sides. So that would be x plus y plus y, or 2x plus 2y would be the more concise way of writing that. And this is equal to 20. All right, so there's my constraint equation. Next, we can come up with an objective equation. Now remember, the objective relates to the thing we're trying to achieve, the thing we're trying to maximize or minimize. In this problem, we are asked to maximize the area. So we should be thinking like, okay, area of what? Well, we've got this rectangle, right? What's the area formula for a rectangle? It's just length times width. And with our variables x and y, that would just be x times y. So our objective equation will just be area is equal to x times y. And I usually make a note in this problem, I want to maximize the area. All right, pretty good. So the next thing is we want to rewrite this objective equation in terms of a single variable. So x we could go with. You could do it in terms of y as well. It's totally arbitrary which variable we try to eliminate. But yeah, I feel like usually we like expressing things in terms of x. So here's what we're going to do for our rewrite. Remember, our constraint equation is 2x plus 2y is equal to 20. We can now solve for one of the variables in this equation and then substitute back into our objective function to get it all in terms of a single variable. So let's do pretty much the same thing we did for the last problem. Let's get y by itself. 2y is equal to 20 minus 2x. And I can divide both sides by 2. So y is equal to, I can simplify this by splitting it up into two fractions. 20 over 2, which is just 10, minus 2x over 2, which is just x. All right, so here is y expressed in terms of x. Now I'm going to substitute into my objective. So the objective now is going to be a of x, because I'm only in terms of the variable x, and it'll be x times 10 minus x. Okay, really doesn't look too different from the last problem. So now I want to maximize area in this problem. So I'll be finding critical numbers, finding a derivative, finding critical numbers, doing a little sign analysis. So let's do that. So this is the actual maximize a of x step. So a of x, I'll distribute the x. 10x minus x squared, so then my derivative a prime of x will be 10 minus 2x. I can take this up here, find some critical numbers. Critical numbers are where the first derivative is undefined or equal to 0. This is a linear function. It's not undefined anywhere. The domain is all real numbers, so we'll set it equal to 0 to find where the derivative is 0. And we will find that x is equal to 5. All right, so our critical number is 5. Now we need to test by doing a sign analysis of a prime. But we can do this quickly. So our critical number is 5, and we want to know the sign of a prime. And what we're hoping for is a maximum, right? Because we're wanting to maximize the area. So I'm hoping to have a maximum at 5. But let's test and see what happens. If I plug in, we could use test values 4 and 6. I always just use whatever the easiest numbers are, integers to the left and right of my critical number. And I'm plugging into my derivative. So I'm plugging into a prime of x over here. If I put in 4, I'm going to get a positive number. I think I get positive 2 out. If I put in 6, I get out a negative number. I get out negative 2. So the behavior of the area function, so the graph of A is going to be increasing to the left of 5, decreasing to the right of 5. That shows that I get a local maximum at x equals 5, which is great. That's what I was hoping for. I'm trying to maximize this area. So, all right, that's good. X is equal to 5. So what is y then? Just like before, I'll plug into my constraint equation, but you know what? I'm actually going to plug into this version of the constraint over here, because y is isolated on one side of the equation. I could just plug in x equals 5 and really quickly get the y value. Because for this problem, I'm asked to find the dimensions of this rectangle. I want the x value and the y value. So a lot of times, this step at the end of the rewrite, or I guess in the middle of the rewrite where you've gotten y isolated in your constraint equation, this is usually the good place to plug in at the end of the problem to get the other variable. So let's do that. Y is equal to 10 minus x, which is equal to 5. So it looks like y is equal to 5. And our units here are important. This was all in terms of inches. All right, so we were asked to maximize the area of a rectangle with a perimeter of 20 inches. So we have a maximum area of length times width. So 5 inches times 5 inches, right? Those are the dimensions. Multiplying those together to give us the area is going to be 25 inches squared. All right, remember when we multiply together to get an area from just the x and the y, we multiply the numerical values, but we also multiply the units together. And inches times inches gives us inches squared. All right, so for a lot of these application problems, we're going to have units to keep track of. So, similarly to in previous sections, at the end of the problem, you want to do a check and make sure that you're providing your answer, including units, sort of in accordance with how everything was defined in the problem. All right, and now we know that for a rectangle with a perimeter of 20 inches, really the one with the largest area is going to be a square. Okay, example number 3. I like this one a lot. This is very, very common. I think if you take a calculus class anywhere in the world, you'll be doing optimization and you will see a problem that looks like this one. By cutting away identical squares from each corner of a rectangular piece of cardboard and folding up the resulting flaps, the cardboard may be turned into an open box. If the cardboard is 16 inches long and 10 inches wide, find the dimensions of the box that will yield the maximum volume. Okay, so right away I can tell I'm trying to maximize volume. So my objective equation is going to involve volume of a rectangular box. So that'll be length times width times height. But we'll definitely want to draw a picture for this one, because what's being described here is, starting with a flat piece of cardboard, cutting squares out of the corners, and then folding up the flaps to make a box. So let's make sure that we understand that part. So starting with a rectangular piece of cardboard. Okay, let's say it looks like this. And we're told that it is, the dimensions are 16 inches and 10 inches. And what we're doing here is we're cutting out identical squares from each of the 4 corners like this. So we can imagine taking scissors or a knife and cutting out those squares. And then, okay, what does it look like after we do that? After we cut out those squares, then we have a shape that looks like this. Okay, just doing my best to draw it out here. Okay, and then we want to fold up these resulting flaps. So you can imagine, making a crease right here, crease right here. And then we fold up each of those flaps and we get a box, an open top box that looks like this. Okay. So I hope that that's kind of clear what happens here. We cut out those squares, we have these resulting flaps, we fold up the flaps, and then we get an open top box that looks like this one. And what we're trying to maximize is we're trying to maximize the volume of this box. So what's interesting about this problem is we don't really need to have a constraint equation for this problem. We can jump straight to the objective, but we have to define a variable somewhere in this original picture and think how we can define the volume in terms of that variable. But it's only going to be one variable. And this is because, really the variable is what are the sizes of these identical squares that are cut out from the corners. So the variable I might define is, how about I call this x? So x is just the measurement of one of the sides, one of the edges of these squares that are cut out from the corners. So it's going to be the same measurement across this whole picture. You could say that the dimensions of the squares that we're cutting out are x inches by x inches. So we don't know what x is. We're trying to find that ultimately. But the question now is okay, the volume of this box, because we know our objective, I'll write it over here, our objective is going to be this volume function, which we can express in terms of x. But before we do that, the volume of a box is length times width times height. Okay, so marking on the picture over here, length times width times height. So these three edges. And then the height is just that dimension there. So we have to think, like X is the size of the cutout. The piece of cardboard was originally 10 inches by 16 inches. How do I define these three dimensions in terms of my variable X? Well, I think the first one that kind of comes to mind is the height. Because remember, the size, like this height right here, is going to be the same as this measurement, right? The size of that cutout, which we know is just X. So the dimension height is just going to be X. Now, how about the length and the width? Well, how about let's focus on this long edge first. Originally, it was 16 inches. So if we look at the previous picture, this measurement from here to here was 16 inches. Now, this edge is not going to be 16 inches. It's going to be a little bit smaller because remember, we have to subtract the width of this flap and this flap over here because both of those got folded up. Since each of those is X inches, that means that this long edge over here is just going to be 16 minus X minus X. And it'll be in terms of inches. I could simplify this to just 16 minus 2X. Okay, so if that's 16 minus 2X, what is this one going to be over here? Well, this edge was originally, looking at the piece of cardboard, was 10 inches wide. And then we folded up two flaps, each of which had a width of X inches. So this is going to be same kind of thing, 10 minus 2X. So the volume I can now express as V of X. Length times width times height is just going to be the product of those three dimensions I just wrote off to the right. So it'll be 10 minus 2X times 16 minus 2X times the height, which is just X. So here is my objective function, and I want to maximize that. Okay, so this one's a little tricky because we don't actually have a constraint. Like I said, this is sort of like a constraint by picture type problem. But like I mentioned, this is a very common type of problem. So whenever you're reading a problem on homework or on a quiz or on a test, as soon as you see this cutting away identical squares from each corner of a rectangular piece of something, you know right away it's going to be this picture. Okay, and you know right away that your volume function is going to look something like, some number minus 2x, some number minus 2x. Okay, so once you've seen one of these problems, you've seen them all. Okay, but now kind of resuming the process or the guidelines that we outlined on the previous page, I want to maximize this volume function. So I'll want to find the derivative, I'll want to find the critical numbers, I'll want to do a sign analysis and figure out the local maximum value for this function. Okay, and we can assume that X is a positive number, right? Because it wouldn't make sense with the application to have a negative X value. We can also assume that X is, it can't be bigger than 5, right? Because if we cut out a number, like a square that's larger than 5 inches by 5 inches, we're not going to have a flap right here, right? Because this edge is only 10 inches long. Okay, so just trying to set some kind of boundaries for what this X value can be. But let's just kind of go through the process here. So we want to find the derivative of this. How do we want to differentiate v? You could do some product rules. You could multiply it out. I think I might just multiply this out. Okay, so I'm going to multiply. I can start by foiling out these two factors together, and I'll get 160 minus, so that's first outer will be negative 20x minus, multiplying the inner together, minus 32x, and then plus 4x squared. All right, and then we still have that factor of x. And then I could just simplify, combine like terms. I could also distribute that x in. Here's what I get. 160x minus 52x squared plus 4x cubed. So here's my function, just written as a, multiplied out polynomial, and this makes it easy to find the derivative. V prime of x will be 160 minus 104x plus 12x squared. Since I'm going to set this equal to 0 and solve, I might write this in general form. And I get that. And now it's time to find some critical numbers. So let's set this equal to 0 and solve. All right, I'll solve by factoring. I'm noticing that there's a common factor of 4 between all these terms. I'll pull out a 4, and then I'm left with 3x squared minus 26x plus 40, just to get those numbers a little bit smaller. And I want to factor this now. The leading coefficient is 3, so factoring it, I'll do one of these things. What two numbers multiply to 120 and add to negative 26? I think negative 20 and 6 are going to do it. Sorry, negative 20 and negative 6. Those two multiply to 120, add to negative 26. Okay. 0 equals, I can divide both sides by 4 to get rid of this 4 right here. Right, because you divide 0 by 4 and you just get 0. So all good, that can go away. I'll split the middle term. So 3x squared minus 20x minus 6x plus 40. And I can factor by grouping. I'll pull out the greatest common factor between these first two, which is just x. Then I'll have 3x minus 20. Greatest common factor between the last two terms is going to be negative 2. And I'll have 3x minus 20 again. I got those matching factors there, so I'm happy about that. I can pull that out. I get 3x minus 20 times x minus 2. So my two critical numbers are x equals 2, and I could set this equal to 0. 3x minus 20, set it equal to 0. Add 20 to both sides, divide by 3. X equals 20 over 3. Or, writing this as a mixed number, this will be 6 2/3. So this time we have two critical numbers. And we're looking for the value of x that maximizes this volume. So the one that maximizes that v of x function. So here the sign analysis is going to be a little more interesting. So let's do a sign analysis now. So here's my sign analysis of v prime of x. I'll do a little number line. My critical numbers are 2, and then 3, 4, 5, 6, 7. So 6 2/3 is going to be around here. Okay. So some test values that I can use. I'll probably just go with 1 and 3 and 7. You know, that'll test each of those 3 intervals that I'm seeing appear here. And I want to know what is the sign of v prime. That'll tell me where my volume function is increasing, decreasing, and so on, so I can find the local maximum. That's what I'm after this time. Okay, so we could use these test values. And remember, I'm just plugging in. You could always do a little table of values, like I'm just plugging into v prime of x. And I'll plug in 1 and 3 and 7. And, you know, I'll see what numbers I get out from that. Okay, and I'm plugging into this up here. Okay, so I used my calculator, and what I found is that when I plugged in 1, I got out a positive number. When I plugged in 3, I got out a negative number. When I plugged in 7, I got out a positive number. Okay, so the behavior of v of x, you know, our function that we're really interested in, it goes from increasing to decreasing through this interval from 2 to 6 2/3, and then it increases again to the right of 6 2/3. That shows that we have a local maximum at x equals 2, and we have a local minimum at x equals 6. But really, we want to maximize the volume. That's what we are asked to do here. So x equals 2 is the value that we want. So maybe I'll put a little purple cloud around 2. This is the one that we want, because that maximizes volume. Very good. So now that we have that, we'll finish up the problem over here, because I always have to go back to the problem and reread it and just ask, like, okay, what specifically is it asking for? Is it asking for the maximum volume? Is it asking for the dimensions? Like, how are we going to provide our answer here? And I see here in the last sentence, we want to find the dimensions of the box that will yield the maximum value. So up here, we're just kind of finishing up the problem. Let's find those dimensions. Okay, so the dimensions, it's going to be length times width times height. And we know that x is equal to 2. That was the height. And what are our units again? Looking back up here, everything was given in terms of inches. So I know that the height is going to be 2 inches. The length, you know, we could say that that's like this dimension right here. So the length will be 10 minus 2x inches, where 2 is equal to 2. The width will be 16 minus 2 times 2 inches. And then the height is just 2 inches. That's the one we've already found. And by the way, the order in which you provide these it doesn't matter. You can do it in whatever order you want. As long as you have all three of those numbers, I'll be happy. So simplifying this, 10 minus 4, 6 inches. By 16 minus 4, that's 12 inches. And then by 2 inches. So these are the dimensions of the box which will maximize the volume. And that's what your answer should look like. You got to include those units. I'll definitely be taking off points if you just write, 6 by 12 by 2 or something like that. I want to see your answer provided in this way. Again, I don't care if you say 2 inches by 6 inches by 12 inches. The order there doesn't matter. But make sure you have those three numbers. Okay. And one more thing I want to point out before we move on is this other critical number, it ended up giving us a local minimum, so it wasn't of interest to us. But what would happen if we tried to, make cutouts that were 6 2/3 inches wide, looking back to our original picture? Well, if this whole length right here is 10 inches, and I made a cut here that was over 6 inches, and I made a cut over here that was also over 6 inches. See how that would not make any sense at all? Like, we wouldn't have a flap at the end of, making those 4 cuts at those 4 corners. So that's kind of a nonsensical answer anyway in terms of the application. So I'm not surprised at all that that critical number was not relevant or useful or a part of our answer. Okay, so it helps. It pays to be aware of these little physical constraints of the problem, just really understanding the picture that you drew at the beginning of this journey. Okay, but this is a great problem to study from. I promise you will see this on homeworks and quizzes and tests probably. So this is a great one to study from. Please let me know if you have any questions or concerns about this process. Okay, and then up next we have a business problem. So for this one, let's read through it. A manufacturer of office fans determines that when X thousand fans are produced each week, they'll be sold at a price of P of X and little linear function here, 44.4 minus 2.4x dollars per unit. Just highlight these units here. The total cost of producing X units will be C of X equals 0.8x squared plus 6x plus 80. Okay, so that's the cost, presumably in terms of dollars, because we saw that up there. So what are we trying to figure out here? How many fans should be produced in order to maximize profit? Seems like a pretty obvious application of optimization, maximizing profit. What will the maximum profit be? And for part B, we want to know how many fans will be produced to minimize the average cost. What is the minimum average cost? And then at the end, we want to figure out how many fans should be produced to ensure that the average cost per unit equals the marginal cost of production. Okay, quite a bit to sort through here. But we know what this stuff means. We know how to find a profit function, because remember, the profit function is always just going to be the revenue minus the cost, right? It's the amount of money that we can bring in this business minus what we have to spend to run the business. So profit, P of X, this is always R of X minus C of X. And breaking that down a little bit more, because we're given a cost function, but we aren't given a revenue function. But revenue is just the price per unit times the number of units that we sell. So this is just x times p of x minus c of x. And remember, profit is usually capital P, and price is lowercase p. That's how I usually do it. So let's plug in our values here, because I would love to get a profit function here. So this will be x times 44.4 minus 2.4x, and we're subtracting from that cost function, which is 0.8x squared plus 6x plus 80. All right, and we can simplify this. We would distribute the x, take the difference, all that stuff. I'm just going to give you what I got after simplifying. Negative 3.2x squared plus 38.4x minus 80. Now this is an optimization problem, and we're asked to maximize profit. So our objective function is just going to be the profit function, which is what we just found. So this is our objective. So given an objective function, how do we maximize it? Well, we've done this a whole bunch already. We are going to find critical numbers, do a sign analysis, find the local maximum over our domain. So how about we find the derivative? P prime of x, that's capital P for profit. I'm getting negative 6.4x plus 38.4. That constant value drops off. All right, so let's find critical numbers now. I'll set this equal to 0. How about add 6.4 to both sides, or sorry, 6.4x to both sides, divide both sides by 6.4, and I get that x is equal to 6. Kind of a nice number there. This is a good opportunity to mind our units. 6 what? 6 fans? No. 6,000 fans. So I'm just going to write that in here to try and stay grounded here. 6,000 fans. All right, but this is our critical number. We have to do a quick little sign analysis to confirm that this maximizes our profit. Wouldn't it be a shame if we did all this work and ended up finding the number of fans that minimized our profits instead of maximized? How bummed would our boss be? We want to maximize that. So let's do a sign analysis. And we just have that one value to test, so I'll do a little number line here. Critical number is 6, so I might use 5 and 7 as my test values. And I'll be plugging into the derivative p prime, so we can see what is the sign of p prime. All right, so we'll be plugging into this function here. If I plugged in 5, I did that, I got out a positive number, and I plugged in 7, and I got out a negative number. So the profit function, profit is increasing to the left of 6 and decreasing to the right of 6. So we have a local maximum. Good. So that's confirmed. Our boss will be happy to see that we're actually maximizing profits rather than minimizing them. That would be a tragic mistake. So we've already answered the first part. We've answered this. How many fans should be produced in order to maximize the profit? 6,000. What will the maximum profit be? All we have to do is plug into our profit function. So P of 6 is going to be negative 3.2 times 6 squared plus 38.4 times 6 minus 80. And I simplified that down to 35.2. And the units of this value is given, if we look at how our functions are defined earlier in the problem, and it isn't written on my page, it will be written on your page. This cost function, C of x, this is measured in thousands of dollars. Okay. And our profit function is going to be the same because, if C of x is measured in thousands of dollars, and then our revenue function, this came from price, which is price per unit, times times x, which is measured in thousands of fans. This is also going to be measured in thousands of dollars, this whole function, P of x. Okay, so that's all to say that this 35.2 is measured in dollars, more specifically thousands of dollars. So here's how I'll write out my answer. I'll say that a max profit, so maximum profit of $35,200. So just taking that last value that I found, multiplying it by 1,000. So that profit is achieved when 6,000 fans are sold. And I'll box that up. Okay, so that's it for part A. For part B, we're being asked how many fans should be produced to minimize the average cost per unit. What is the minimal average cost? So this is another thing that would make sense to do if you're running this business. How can we minimize the average cost per unit? Well, remember the way that we define the average cost, I'll just call it AC of X. It's defined as the cost. So the cost function C of X divided by the number of units produced, divided by X. So we essentially want to minimize this function. So we'll plug in what we have for C of X and figure out what the average cost function is. And then we can find a derivative and find its local minimum. So let's do that. Plugging in C of X, I have 0.8 x squared plus 6x plus 80, and this is all divided by x. And you could leave it like that as your average cost function, but I think I'm going to divide through that x just to make it easier to find the derivative. I can write this as 0.8x plus 6 plus 80 over x. Okay, so this sort of becomes our new objective function. So now the average cost function is our objective and we want to minimize it. So let's find the derivative. AC prime of x will be 0.8. The 6 goes away because it's just a constant. And then taking the derivative of 80 over x, I'm going to get minus 80 over x squared. All right, the steps in between, remember, we can rewrite this as 80 times x to the negative first power. So just doing a power rule, we get negative 80 x to the negative second, right? So that's where that last term came from there, just taking the derivative of 80 over x. So there is our derivative. Let's minimize the average cost using that derivative. And I'll want to set that derivative equal to 0. And solve for x. So how about add 80 over x squared to both sides? And I can multiply both sides by x squared, divide both sides by 0.8. And I end up with this. So I get that x squared is equal to 100, taking the square root of both sides, x equals 10. Okay, so that's one critical number. We actually have an additional critical number because this derivative is undefined when x is equal to 0. So technically we have another critical number at x equals 0. However, this is not super relevant or helpful because this is just like what's happening when we're producing 0 units, which is not, it's not a relevant value. It is an endpoint, which does give us a critical number, but we're trying to find the number of fans that are produced to minimize the average cost. Obviously, not producing any fans at all isn't going to be the number we're looking for. So we'll disregard this one. But let's test x equals 10. I'll do a little compact sign analysis right here. Okay, testing the derivative AC prime of x. And I could plug in 9, I could plug in 11, and when I put in 9, I got a negative value. When I put in 11, I got a positive value. So that means that the average cost is decreasing to the left of 10, it's increasing to the right of 10. All right, so we have a local minimum, which occurs at x equals 10. Which is good news because we were trying to minimize. So I'm glad that we found a local minimum. And this x value 10, remember this represents thousands of units. So I'll say average cost is minimized when 10,000 units are produced. Okay, and then that minimum average cost we can get by plugging in, so AC of 10. Okay, so we'd be plugging into this over here. And I did that and I got 22. So the units for this is going to be $22 per unit. Okay, and remember, average cost is always going to be a rate like that, because if it's an average cost, it's going to be, but whatever the denominator is. This is going to be like the number of units. And the numerator is going to be the cost, which will be, some unit of money. In this case, it was like thousands of dollars over thousands of units. Okay, so that's why we ended up with dollars per unit. Like you could say $22,000 per 1,000 units, but I'd rather just say $22 per unit. Okay, so we're basically just applying the same procedure to a different function here, which we can find. Part C, last part. How many fans should be produced to ensure that the average cost per unit equals the marginal cost of production? So remember, the marginal cost is just equal to the derivative of the cost function, so c prime of x, which is take this derivative, I get 1.6x plus 6. That just coming from the derivative of our cost function up here. So if we want to ensure that the average cost per unit is equal to that marginal cost, we just want to set this marginal cost, c prime of x, equal to that average cost per unit of $22 per unit. Okay, so substituting in my derivative 1.6x plus 6, and I'm setting this equal to that minimum average cost of 22. Solve for x. I'll subtract 6 from both sides. And divide both sides by 1.6. I get that x is equal to 10. All right, and remember, x is measured in terms of thousands of units. So average cost will be equal to the marginal cost when 10,000 units are produced. Okay, very good. We've got one more box problem that deals with optimization before we move on to something a little different. But let's read through example 5. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of materials used. All right, so this type of problem makes a lot of sense. We could understand why a manufacturer or a shipper would want to be able to solve a problem like this, right? We need a certain amount of space for whatever this thing is that we're shipping. It would make sense to optimize the amount of materials used, whether you're building a cardboard box or a plastic box or a wooden box or whatever. And fortunately, we can use calculus and the derivative to answer this type of question. So first, let's kind of make sure we understand what's going on here and make sure we understand what a square base and open top means. So this box, the base is square, meaning that the two sides on the bottom are going to have the same measure. Okay, so our box, I'll draw it to be kind of tall. We don't know exactly what this box looks like. But the important thing to understand is that these dimensions, this one right here and this one right here, are going to be equal to each other. So we can label them, we want to set up variables because obviously like all the dimensions of this box are going to be variable. We could just call this x, how about? And since this is a square base, this side will also be x. And our units are going to be centimeters, right? Because the volume is given in centimeters squared, so it would make sense to put everything in terms of centimeters. Okay, so that's the square base part. Open top means that there is no lid on this box. So, really to make this drawing accurate, I should make that back corner visible because there isn't a top on this box. So we're not having to account for the top. We're just thinking about those four sides and the bottom panel. All right, so that's the only part of the box that we actually need to have covered with material. Okay, and there's obviously one more unknown dimension here, the height, which I'll just label with a y, how about? And of course that will also be measured in centimeters. Okay, so we should now be thinking about, all right, what's our constraint? Do we have a constraint equation? What's our objective equation? What are we trying to optimize in this case? And it's pretty obvious in this problem, I think, compared to some of the others. Remember the constraint, if there's a number that's given in the problem, oftentimes that defines the constraint. And that is the case in this problem. We must have a volume of 32,000 cubic centimeters. So my constraint equation the volume of this box must be equal to 32,000. Okay, but what is the formula for the volume of a box like this? Well, normally volume is length times width times height. What's the length, width, and height of this box? Well, length and width are both x, and height is just y. So the formula for volume is going to be x times y, and that will be 32,000. I can simplify this to just x squared y equals 32,000. Okay, and I'm happy with that for now. Notice that in this problem, the constraint is the volume. I think in the other box problem that we've seen, the volume was actually the thing we were trying to optimize. So it's kind of flipped in this problem where we're not optimizing volume here. That actually gives us the constraint. But what is our objective in this case? Our objective equation is going to be the thing that we're trying to optimize, and this last sentence shows that we want to minimize the amount of materials used. So how do we represent the amount of materials used given our picture here? Well, if we're talking about, having some material to cover the sides and the bottom of this box, I was saying like, oh, cardboard or wood or plastic, something like that. Like, how would we measure the amount of cardboard if that was the material we were talking about? Well, cardboard comes as like a flat piece, then we would cut it up in such a way that, we'd be able to construct this box. So really we're talking about area here. We want to know the area of cardboard or plywood, same thing. So specifically, since we're constructing this box, we can call it surface area. So amount of materials used, that's going to be measured in terms of surface area. And the units of that will be centimeters squared, right? Because volume is centimeters cubed, area is centimeters squared. So our objective function is going to be a surface area function. So I'll just label it SA for surface area. And what is the formula for the surface area of this here box? So it's important to note that we don't have a top, right? So that sixth side of this box doesn't need to be accounted for in this equation. Really, we just want to add up the surface area of each of the 5 panels that we have on this box. So let's just add them up. You know, the bottom panel, what's the area of that bottom panel? Well, it's just going to be x times x. And then we'll add that to the side panel, and there's 4 of them, right? And each of them has an area of x times y, right? So like if we're looking at, whoops, just messing my whole picture up here. One of these panels, I'm just using my highlighter to show you, one of these panels, the area of that is just going to be length times width, so x times y. And there's 4 of those panels. So we're going to do 4 times x times y. Okay, just to be extra clear what's going on, that's the area of the base. And that gives us the area of the 4 sides. Simplifying a little bit, I can write this as x squared plus 4xy. That looks pretty good. Now we have our constraint, we have our objective. I think we're ready for the rewrite step. I'd like to express this objective equation in terms of just one variable. So then I could just have it as like a function in x. And you probably know where we're going with this. I'm going to take my constraint equation, which was x squared y equals 32,000. I'll isolate one of the variables. Y is looking like an easy target here. Just divide both sides of the equation by x squared. So here's our rewritten constraint, and I can now take this 32,000 over x squared and plug it in for y in my objective. And this is good because now we're going to have surface area of x. This is a function just in x now, and it'll be x squared plus 4x times y, but I'm substituting in 32,000 over x squared. Okay, this is great. This is where we're trying to get, because now we just have to find a derivative of this, find critical numbers, do a little sign analysis, and find the value of x which minimizes that surface area. So let's go ahead and, so this is the minimize step. Let's find the derivative of our surface area function. I'll get to, you know what, actually, sorry, let me simplify a little bit. I can leave this as x squared, but I can write this as plus, so 4 times 32,000, I get 128,000, and then an x in the numerator cancels with an x in the denominator, so I get 128,000 just over x. Because of those common factors. All right, and if you wanted to, I'm inclined to rewrite this one more time as x squared plus 128,000 times x to the negative first power, just to make it easy to do a power rule. So finally I can find my derivative. I'll get 2x minus 128,000 over x squared, like that. Okay. And we can find our critical numbers for this. Keep working up here. Critical numbers, so for what values of x is this derivative equal to 0, or where is it undefined? I can tell you right away that we have a critical number at x equals 0, because it'll make that function undefined. So x equals 0 is one of them. But let's set this equal to 0, set the derivative equal to 0. And solve for x. Okay, and this is a little bit of a tricky one. There's a few different ways that you could proceed here. But what I think I'll do is I'll solve this one by factoring. So if I factor out 1 over x squared, I'll be left with 2x cubed minus 128,000. I guess I could bring out a 2 as well. And then I'll just have x cubed minus 64,000. And you can set each of those factors equal to 0. Okay. This, of course, is undefined, so we don't get one from here. This is just, the x equals 0. Over here, we can take a cube root. So get 64,000 on one side. And take a cube root. So x, in this case, will be positive 40. Which is a very nice number. All right, and then of course we do a little sign analysis. I'm gonna sort of gloss over that, but you would do a sign analysis. Using these critical numbers, x equals 0 is not super relevant as a critical number, because if x equals 0, then we don't have a box, right? The dimensions of this box would be 0 by 0 by, I don't know, infinity. So this is not really a relevant critical number. Really, we're interested in 40, so we could do a little sign analysis. But I'm going to spoil it, and I'll just tell you that when you look at this, and you're looking at the derivative, you will see that it is negative on this side, positive on this side. So we do, in fact, have a local minimum. Okay, so x equals 40. That's going to be 40 centimeters, that is. That's going to be the dimension of, the base. It'll be 40 centimeters by 40 centimeters. And to find y, we can just plug into our constraint equation, particularly this constraint equation where we have y isolated. I always look to that. So y would be 32,000 divided by 40 squared, which gives you 20. And that'll be in terms of centimeters. So to give the answer in the form that it's requested, we want to find the dimensions of this box. And here are the dimensions. It's going to be 40 centimeters by 40 centimeters. That gives us the square base times 20 centimeters. That's the height. So there is our answer. Okay, so I hope you see this process is really quite uniform for a lot of these problems. Find the constraint, find the objective, rewrite it, do the optimization step, do a little sign analysis, and then just figure out how you want to give your answer. Okay, so this is a great problem to study from. You'll get a chance to practice this on homework. So moving on, this is the kind of last topic of this section and of this chapter, elasticity of demand. So let's have a look at this little passage here. In general, the demand for a product tends to be affected by fluctuations in the price of the product. However, the degree of change in demand will vary greatly depending on the product. For example, the demand of gasoline will not vary much if there is an increase in price, since transportation is so essential to the functioning of society, right? We kind of have to put gas in our cars no matter how much it costs. That's why it's such a big deal when it goes up a lot. On the other hand, if there are significant increases in the cost of a home loan, right? Like if interest rates go up, like we have experienced recently, you could see a sharp decline in the demand for new homes or for new loans, since you can always just opt to rent instead of buy. Okay, so it makes sense. Or if like a particular fruit, like you might love mandarin oranges, but if they go up to $6 a pound at the grocery store, you might just not buy mandarins. You might just buy navel oranges instead, right? So the degree to which the degree to which the demand is affected by increases in the price is what we call elasticity of demand. And we have a pretty nice little function to express elasticity of demand in terms of a derivative of the demand function. So if Q, we're going to call this our demand function, this is D of P. So if that many units of a commodity are demanded by the market at a unit price of P, where this will be measured in dollars in most cases, or whatever your currency is, where D is a differentiable function, then the price elasticity of demand for the commodity is given by E of P. That's how we label the elasticity function. And it's defined as negative P over Q, so that's price over the demand function times the derivative of the demand function. All right, and that'll be with respect to our independent variable P. The value of E of P can be interpreted as the approximate percentage rate of decrease in demand produced by a 1% increase in price. Okay, so if E of P is a large number, specifically larger than 1, that means that we have a product which is more sensitive to changes in price. So that's what we're looking at here in levels of elasticity. If E of P is greater than 1, then the percentage decrease in demand exceeds the percentage increase in price. Thus, the demand is more sensitive to changes in price. In this case, when E of P is greater than 1, we say that demand is elastic. And revenue R will decrease as price P increases. If E of P is less than 1, then that means that the percentage decrease in demand is below the percentage increase in price. Thus, demand is less sensitive to changes in price. In this case, we say demand is inelastic. And revenue R will increase as the price P increases. So if we are in this situation where we see that the demand of our product is not very sensitive to price increases, then it would make sense to increase the price, right? Because our revenue is going to go up if we increase our price. Okay, but if we increase the price P too much and we get into this place where demand is all of a sudden elastic, then our revenue is going to decrease as we increase our prices. So it would make sense to try to get our elasticity function, our E of P, to be equal to 1. Okay, because in this case, the percentage decrease in demand is approximately equal to the percentage increase in price. And in this case, we say that demand is unitary. Or sometimes we say of unit elasticity. And revenue R will be unaffected by as the price P increases. Okay, so we're trying to achieve this generally. Okay, so a little note here. Note if E of P is equal to 1, revenue is maximized. Okay, lots of information here, but let's look at an example and see how we can apply all of this theory to an application. So a company finds the demand Q in thousands for their kites to be Q, and it's equal to this quadratic function 400 minus P squared at a price of P dollars. Okay, so the independent variable is the price. That's the thing that can fluctuate. And Q, demand, is going to be the dependent variable. It depends on the price. So we want to find the elasticity of demand when the price is $5 and when the price is $15. So we're essentially given two different P values, P equals 5 and P equals 15. And we want to find E of P for each of those values. So I would recommend first figuring out what is E of P. Like, we have to figure out what is this elasticity function, E of P, and we have a formula for it. It is equal to negative P over Q times dQ dP. So let's substitute in what we have for Q. So we'll leave this as negative P because P is our independent variable here. This will all be in terms of P when all is said and done. Q we can replace with this expression that we're given, which defines Q in terms of P. So Q, I'm going to substitute in 400 minus P squared times, now we want to multiply by the derivative of Q, so take the derivative of 400 minus P squared, and we just get negative 2P to the first power. So just applying a power rule to this over here. And of course, I will simplify this a little bit. So E of P, I can simplify this to positive 2P squared divided by 400 minus P squared. Okay, so just combining that product there. And we have this relatively friendly looking rational function here. So here is our E of P. So now we want to evaluate this at 5 and at 15. So that's what we'll do over here. So let's do 5 first. So E of 5 is going to be 2 times 5 squared divided by 400 minus 5 squared. Up top we'll have 2 times 25, that'll be 50, divided by 400 minus 25, that's 375. So you could leave your answer, you could simplify this, reduce the fraction, but I actually want a decimal. I put this into my calculator and got approximately 0.1333. We have a repeating 3 there. And the reason I put it in my calculator to get a decimal approximation is because I want to know how close this is to the number 1, right? Because remember, we would like to achieve, in order to optimize revenue, E of P equals to 1. Okay, so depending on how close, or how, if this is larger than or smaller than 1, that'll tell us about the elasticity of demand given this value of P. So we see here, of course, that E of 5 is less than 1. So what does that tell us about demand when the price is $5 per kite? Well, since its number is less than 1, that tells us that demand is inelastic when P is equal to 5. Okay, so I'll just say that when P equals 5, demand is inelastic, meaning it isn't overly sensitive to changes in price. So if I were the accountant for this kite manufacturer, I might say, hey, we want to increase the price. We can go higher than $5. So next step, let's test 15. Should we charge $15? Is that enough? Is that too much? Let's find out. So E of 15, just plugging into the same function, 2 times 15 squared divided by 400 minus 15 squared. I used my calculator. Admittedly, I don't know what 15 squared is. I got 450 in the numerator divided by 175. I can definitely see this number is greater than 1. I put it in my calculator and got approximately 2.571. And this, of course, is greater than 1. So we can see that when the price per kite is $15, demand is elastic. All right, meaning that any further price increase from here is going to have a disproportionate effect on demand, which we don't want. Okay, but for part A, we are really just asked to find the elasticity of demand, and that was these two numbers here. Now, for part B, unsurprisingly, we want to find the price P that will maximize revenue. And we can use our elasticity function to do that. We just want this to be equal to 1. So for part B, we simply want to set E of P equal to 1 so that we can achieve unitary elasticity of demand. So I'll plug in my function here. I have 2p squared divided by 400 minus p squared. Set that equal to 1. All right, and how might we solve this equation here? Well, I don't really like this fraction, this rational function equal to 1. Let's multiply both sides of the equation by 400 minus p squared. I'll just write this step out, because what happens is, we could put this over 1 here, and we get this cancellation, 400 minus p divided by 400 minus p. All right, just assuming that p is not equal to 20, right? Because then we'd have 0 in the denominator. But anyway, that cancels out. We get 2p squared is equal to 400 minus p squared. I like the look of this equation a lot more. This is just a quadratic equation, which I'm much more comfortable solving. I think the most straightforward way to solve this would be to solve by taking square roots. So what I'll do is I will add p squared to both sides. So now I'll have 3p squared is equal to 400. Divide both sides by 3. and then take the square root. Sorry, I'll keep working up here. I ran out of room. I'll take the square root of both sides, and I'll get that P is equal to plus or minus square root of 400 divided by 3. Remember, that entire fraction will be inside of the square root. Technically, it's a plus or minus, but a negative value does not make sense in this application because we're solving for the price we're going to charge per kite. So we're not going to be using a negative value here. So really, we just need the positive one here. And I put this into my calculator, and we'll round to the nearest hundredth because we're talking about dollars here. I got 11.55. So the price which optimizes or which maximizes revenue is going to be $11.55. So a little sentence here, revenue is maximized when the price is $11.55. And this sort of cooperates, or it jives with what we saw in part A, because remember, $5 was too cheap, $15 was too expensive, as far as settling on a price which charges enough money but doesn't deter buyers. So this value, $11.55, falls somewhere in the middle. So this number makes sense to me. So there it is. That wraps up elasticity of demand. That wraps up optimization and chapter 4. So next we're going to move into chapter 5. We'll start talking about the next big topic in calculus, the other part, integral calculus. So I will see you very soon in the next video, section 5.1.